This is day 12 of Advent of Code, and the challenge is called Hill Climbing Algorithm. You try contacting the elves using your handheld device, but the river you're following must be too low to get a decent signal. You ask the device for a height map of the surrounding area, your puzzle input. The height map shows the local area from above broken into a grid. The elevation of each square of the grid is given by a single lowercase letter, where A is the lowest elevation, B is the next lowest, and so on up to highest elevation Z. Also included on the height map are marks for your current position, capital S, and the location that should get the best signal, capital E. Your current position, capital S, has elevation A, and the location that should get the best signal, capital E, has elevation Z. You'd like to reach capital E, but to save energy, you should do it in as few steps as possible. During each step, you can move exactly one square up, down, left, or right. To avoid needing to get out your climbing gear, the elevation of the destination square can be at most one higher than the elevation of your current square. That is, if your current elevation is M, you could step to elevation N, but not to elevation O. This also means that the elevation of the destination squares can be much lower than the elevation of your current square. For example, a bunch of letters here, so if you start at S, you can go A, maybe B. Here you start on the top left corner, your goal is near the middle. You could start by moving down or right, but eventually you'll need to head towards the E at the bottom. From there, you can spiral around to the goal. In the above diagram, the symbols indicate wherever the path exists, each square moving up, down, left or right. The location that should get the best signal is still capital E, and dot marks unvisited squares. This path reaches the goal in 31 steps, the fewest possible. What is the fewest steps required to move from your current position to the location that should get the best signal? Okay, well this sounds like it's going to be a difficult challenge, so let's give it a shot. So let's grab the input, and let's save it here. Okay, where are we? Capital S. That doesn't appear to be a capital S. What about capital E? Okay, there's where we're trying to get to. Where our position is. Wait. Okay, there it is. I'm blind. So we're there, and it's going across to E. So I think it was saying go one at a time. So one elevation at a time. So say this. I think you go B, C. Can't go to A, so you'd have to go like around. It's going to be... Well, let's start off with creating a map. Var map equals list of characters. Then do for each var line in input. Var car list equals new list of cars. We'll then do for each car C in line. Car list dot add C. Then we will add map dot add car list. We have var current position equals int of 2, and we'll then have var destination position equals new int 2. We will then do if C equals S, current position 0 equals car list dot count minus 1, and then current position 1 will be map.count. We'll do the same thing for else destination. I think that was E, right? Yep. And do destination position, same thing. Okay, now that we've created a map, I'm going to just quickly make sure that it is working as expected. Okay, so we've printed out the map and it appears to all be as expected. So it's now for the hard part, where we are now wanting to go from where we currently are and find the path to the destination. So there will be two things I think we'll need for this. We'll need to record the locations we have already been to, and then record the current path that we are on. So we will do var previous locations equals list of ints. Can you do it like that? And then we will have current path equals this. So when we're going down a path, when we're in a position, we're going to look at a first spot to see, okay, can we go to there? If we can, we'll go to there. Then we'll go along. If we can't go to a spot, we'll look at the next spot. We'll go along there. And if we're at a spot where we can't go anywhere else, we're going to backtrack and then go to any other ones we can go to. If you can't, backtrack. And just go along like that. I think that's how we'll have to do it. But so, let's make a start on this. So, trying to think of the best approach to this. So we need to do some kind of loop, but I'm not certain how we would do this loop, because we want it to stop when there are no more paths that we can go down. Or more specifically, we have found... it's when there are no more paths that we can go down. I guess we'll have a bool no more paths equals false. So while not no more paths, we will do... I think for this recursion might be needed. Oh, let's create a function. Void explore paths. So we'll pass in the current position, and we will pass it current path. Actually, we'll just make this global. Actually, not certain the best way to do this. I'm gonna remove this, and we'll just do some pseudocode stuff. So we'll definitely be passing current position. We'll then be doing for int I equals 0, I is less than 4 I plus plus. This will simply just be a counter to indicate which direction we're going to try. So we'll do an if I equals 0, go up, else 1 will go right, down, left. So we'll have an int x equals 0, int y equals 0. These will be the offsets we'll do. So to go up, this will be y minus minus, right will be x plus plus, down is y plus plus, and left is x negative negative. So when we've got our current x and y offset, okay, so looking at this, we'll move map to global, we will move previous locations and current path to global. Okay, I think that should be good for now. So we'll have some checks. If current position 0 plus x is less than 0, or x plus is greater than map 0 dot count, continue. We will do the same thing for y. We will continue. We will also need to check if previous locations dot contains new int current path this, current path this. Okay, just quickly reduce the amount of we have to type. So I'm not sure if we have a list of arrays we can do a contains like this. Let's look up how. Okay, I think this here is what we'll be looking for. So let's just paste that in here, and then we'll import link, and we will do previous locations any l dot sequence equal, and that will equal this. We'll continue. We will also need and then we'll also do the same thing here for current path. So if we go through all this, so we're checking to see if this is a valid location on the map, then down here, already visited location. Then what we need to do now is if location accessible. And something else we're going to do is a list of valid paths, which will be a list of lists, ints, and these will be all the ways we can get to the new location. So we'll just do basically if map x y equals e, I think that's what it is, right? Then valid paths, actually no, we need to, it equals e, current path dot add new int xy, then valid paths dot add current path, and then we can break, I think. Yep. We also need to be checking to see if we have valid characters. I'm just going to quickly write out the alphabet. And what we'll do here is we'll find the index that the current letter is in the alphabet. So the current position we're in, then we look at the next position and find the index of that. If it's one apart, then it's a valid movement location. Okay, so that works. So the way that we will do this is var current car equals map x y. Oh no, this will be current position 0, current position y, and we'll do var next pos car equals map x y, and with this we will do if current car equals s, we will actually, let's see what way it can move. I think it was, if it's capital S, it counts as an A. Okay, yep, same elevation as A. So if current car equals S, we'll do current car equals A. And let's see. Okay, whereabouts is E? E has elevation of Z. Okay, this is the only one we need to do it for. So the way that we will do this is if current, we'll do math.abs. Actually, let's look up how to quickly do that again. Yep, math.abs. This will be alphabet.index of current car minus alphabet.index of next position car is less than or equal to 1. Actually, something we need to do just in case, it's because we're not handling the destination yet with the alphabet. So how do we do this? We'll just chuck capital E here. So if it's less than 1, or next pos car equals E, and current car equals Y, or current car equals Z. Oh, need to do lower cases. Let's move that back around here. If valid movement, and for the sake of just keeping consistent with doing continue, we will do not like that. So this should handle, if the movement is invalid, then it won't move. Then next to here, we will do current path add new int like this, and we'll remove this from here. Yep, so current paths add will break. Then outside of this for loop, we will do current path dot remove at current path dot count minus 1, because then it's going to return to the previous function that's running. As we're going to be doing it recursively, that should work. So we'll do this, and it will break. But if it doesn't break, we will do explore paths with a new int of x and y. So current path. Oh, we need to add it to previous paths as well. But we will do this. This previous locations one doesn't exactly work, because you could take the long way up and you would start over and you'll try and move back there, but then there might be a quick way which requires going on previously used tiles. Not sure about this now. You know what, I'm going to try without the previous locations one. Although this will allow for really long-winded paths, it will eventually solve itself, I think. Okay, so let's go down to here. Actually, we don't need to have we don't need to have this. It just needs to be like this. And we will path the current position. I've got no clue if this is going to work, but I just want to see if it does anything. It's possible because of how large this is. It could take a really long time before it gets anywhere, but let's see. Okay, so line 9, maybe doing this will work. Okay, doesn't seem to. We'll just remove the number length from it. Line 44, oh my bad, this should just be map.count, and line 53 equals. Let's try that. Line 68 was saying index was out of range, must be non-negative and less than, actually saying line 51. Okay, I've got this completely wrong way around. Greater equals, less than. Now let's try it. Index was out of range, must be non-negative. Line 70. Current path dot count is greater than 1. We'll do that. Let's try again. Okay, well that didn't work at all. So does that mean it never found the destination we're wanting? You know, let's do an int run count equals 0, and we will do, every time this function is ran, run count plus plus. Let's see if that does, if we can see how many times it's being ran. Okay, it's only being ran once. Okay, well let's see if there's, at any point, it gets to a valid run path. Actually, better yet, we'll go to here, and we will print out current position 0, current position 1, and we will then print out x, y. Okay, I would have thought this would be fine, so like it should only skip this one. So let's move this print to down here. Let's see what this does. If it prints out the same amount. Okay, it stops here for some reason. Wait, no, this was correct. If it's less than 0, it shouldn't run. If it's greater or equal to map count, then it shouldn't run. Okay, now let's see. I think that was a problem. Let's just comment this out. Let's run again. Okay, yeah, that was a problem, but now there's another issue. Next out of range, line 56. Oh, maybe we should keep this in, just in case. Like, let's run it. Okay, where did the error occur? Occurred here. Yep, so these numbers are too large. How did it get to 41? We are going to print out some more numbers, which will be this and this. Okay, so that is 101 rows and 41 columns. And I'm going to include all these into here as well, just so we can see. Okay, so it's returning false, but we can see here, so this is current position X, current position Y, and this is X, Y. That should be working, shouldn't it? Line 57, so it's this one that's not working. Okay, I have the numbers the wrong way around. So if we go to this, there's 41 rows, not... Okay, we need to reverse it, so it's not XY, it's YX. So the Y is the column, the rows. So that should have been right, shouldn't it? No, wait, the issue is I have the numbers wrong way around. So keep it like this, but we need to reverse these numbers. So a similar thing happened, I'm guessing. Oh yeah, so we need to, for this, switch these around. Ah yes, so this now needs to be Y, X, X. Okay, I'm going to comment this out and see if that fixed it. Okay, I need to re-enable the comment. Oh, the print. So we got to here, similar thing. Oh no, this one's line 69. Ah, no, X, Y, X like that. You know what, we'll just do this all correctly now. So Y, X. It was swapping over each turn. Interesting. From down here, and we call it. Okay, you need to change these as well. So that's Y, X. First index is the Y for the rows, and it's a column. So Y, X, good. Okay, now let's rerun it. Okay, this seems to be promising. Although it's going to be taking a while, as we can see. Although looking at this output, it looks like it's stuck maybe. Okay, I need to stop that. Let's see what's happening. Say 86, it goes one like that, and moves here. So there's an 8539 here, which goes 8540. You know, just for additional logging, we'll remove this. This is no longer needed. And we will remove this, but we will see what the count of the current path is. So let's run that. Let's see. Okay, so it's not 100% stuck. It's just it's gone so far forward that now needs to go backwards. But the issue is because it's so far forward, because there are so many numbers, there are so many possibilities. We might need to figure out a way to record paths that lead to dead ends or something. So then if you go down it, you can avoid it. Now, for the sake of helping push it along, I'm going to rearrange the order that it's done. We want to go right first. Let's just do that. I don't know if this is going to do anything, but I'm willing to give it a shot. So let's see. Okay, I'm going to remove this console printing, so there's just less outputting it has to do. But what we will do is do a console dot right here, and we'll do valid paths dot count, and I'm going to run this, and hopefully if I just let it run for a while, it will find a valid path. So this is just going to be my brute force attempt at trying to figure it out. Okay, I was reading through the instructions, and something I just realized is that if you're going up, the difference can be at most 1 higher, but if you're going down, the elevation of a destination can be much lower than the elevation of your current square. So we need to change this, so if it's lower, then it could be any amount lower. So we should change this to, we can change this to the next position minus the current position is less than or equal to 1. Oh, we already got that there. Yep, so less than or equal to 1, or next position E, and this. Okay, yep. So after spending a few hours trying to figure this out, I am not able to figure out how to do this, so ended up searching for solutions online, and I came across this GitHub for day 2, which is right here. I'll have it in the comments so you can look at it and see the reference. So it's a solution that works pretty well. I'll go through how it works. So we'll start at the bottom here. So same code, creating the map. We have the explore function, which is the way this works is you start at the end location. From there, you go to all the different paths that you can go from here, everywhere else. You save the minimum distance to it. So if you go from like this path to this path, and let's say it took 7 spaces to go there, you then go a different path, and let's say that was 3, you'll then say, okay, this one only takes 3 to get to here. So you do that for every square on the grid, and then right here, you put in your starting coordinates, and then it'll tell you the distance that was saved for it. So that's the main way it works. So let's go to the actual code. So we've got a dictionary, which is of a set tuple xy coordinates, and then has a value of what the distance is. Actually, I just noticed a mistake here. Let's change this quickly. So we've got this explore paths function, which is same one we had before. So with this, you pass in the x and y coordinate. You grab the current distance for this one. So down here, when we find the endpoint, we add it to the dictionary. So you grab that. You then run neighbor cost, which is putting in the coordinates for each one of your neighbors, the neighbor coordinates. So then it goes into here. First, we do a check to see if that coordinate is valid on the map. We then do a check to see if the movement is valid. So as we're working with cars or characters, we can just directly convert them to numbers. So we can do grab the character here +1. If this is greater or equal to the current place we're on, then that means we're able to go from the neighbor cell and move into the current cell. So once you do that, okay, so the first thing we do is check to see if this neighbor cell has a distance count in this dictionary. So if it doesn't exist, we'll go straight to here. Otherwise, if it does exist, we check to see if the value for the distance we have for this cell is greater than the current distance cost we have for it. So if this is true, we then add this value into the dictionary for it. And as we are now on a path which is like the quickest, we then run the explore paths on this cell. So then we'll go back to here and we'll rerun it through. Although looking at this, I wouldn't have thought it would be current cost +1. I might just remove this and see if it still works. Okay, well based on it freezing like that, I'm going to assume it didn't work, so +1. So when we ran this, we got 361, so I haven't actually tested it, so hopefully it is correct. So let's say 361. Yep, so that is part 1 complete. Well, part 1 finished. I wasn't able to complete it as I just got a new value, but hopefully with this as a base, I can now do part 2 by myself. As you walk up the hill, you suspect that the elves will want to turn this into a hiking trail. The beginning isn't very scenic, though perhaps you can find a better starting point. To maximize exercise while hiking, the trail should start as low as possible, elevation A. The goal is still the square mark D, however, the trail should still be direct, taking the fewest steps to reach its goal. So, you'll need to find the shortest path from any squared elevation A to the square mark D. Again, consider the from above. Now there are 6 choices for starting position, 5 marked A plus the square marked S. That counts as being at elevation A. If you start at the bottom left square, you can reach the goal quickly. This path reaches the goal in only 29 steps, the fewest possible. So what is the fewest steps required to move? Okay, so now that we have this, it should be much easier. So I'm going to quickly modify this code. So instead of us having to run this explore paths twice, it'll just run it once. And then we'll also put the map up here. So we build the map once, we do the explore paths once. Now it's just a matter of doing the code for getting the numbers. So we're going to create a list where it starts at A. Let's see, how can you do that? So coordinates, int, we will do for each var row in map, for each var cell in row. Wait, no, this should be for int row equals 0, row is less than map.count, row plus, and then we'll do for int cell equals, int col equals 0, col is less than map row dot count, row col plus. So if map row col equals A, start in A dot add col row, then we will go through int lowest equals int32.max value for coord in start in A. Var count equals distance here, and it will be coord for each. If count lower than lowest, lowest equals count, and then console.writeLine lowest. Let's run part 2 and let's see if this works. Okay, the name call does not exist, line 69, it's 2 L's, no overload for the method add, line 70, needed a second parentheses here, so let's rerun that. The given key 30 was not present in the dictionary, okay, so we will do if distance dot contains key coord, we will continue. So we're doing a check to see if it exists. If it doesn't, just continue running. Okay, 354 is the number we got, 354. And that is part 2 complete. If you like this video, make sure to like and subscribe so you can see me attempt to do more of Advent of Code 2022.